Hello, and welcome to the video lectures on theory of computation. Today we're going to be talking about hardness reductions from 3-set. This is a four-part lecture, and we'll begin with a review of hardness reductions. So let's go over decision problems, their certificates, and the family of problems NP, non-deterministic polynomial time. A decision problem is an algorithmic problem that has a yes or no answer. It might be, does a graph have a large set of vertices that have no edges between them? It might be, does a graph have a cycle that goes through every vertex exactly once? It might be, does a Boolean formula have an assignment to variables such that the formula evaluates to true? The family of NP problems are problems X where every yes input has a short certificate that can be easily verified to be a yes input. So for example, if we have a Boolean formula, to easily verify that this Boolean formula has a satisfying assignment, the certificate would just be the satisfying assignment. We can plug it in and check to see if it evaluates to true. For a graph, where we're trying to see if there's a large set of vertices that doesn't have any edges, the certificate could be the large set of vertices, and we can just check to see if none of the vertices have edges between them. A problem X reduces to a problem Y in polynomial time, denoted X less than or equal to P Y. If there exists an algorithm that solves every instance of X in a small number of basic operations and a small number of black box calls to a solver for Y. And this notation, less than or equal to, sort of indicates harder than. This should be read as Y is at least as hard as X. Okay, and now we'll say a problem X is NP hard if any problem Y in NP can be reduced to X in polynomial time. And what this means is if we have an algorithm that solves X, then we can solve any problem in the family of problems NP. Okay, and this is the family of problems that have short certificates that can be quickly verified. And so this is what NP hard means. NP complete requires two things. It requires the problem X be in NP, and it requires X also be NP hard. And so these are the problems in NP that are as hard as any other problem in NP. Great. And we're going to be looking to show problems are hard by showing they're as hard as any problem in NP. And one way to do that is to give a polynomial time reduction. But it'll be frequently possible to show a polynomial time reduction of a very special form that takes a single call. These are called CARP reductions, or single call reductions, or mapping reductions. And what we're going to be doing in this lecture is discussing how to construct this kind of reduction. And one of the things that's nice about this kind of reduction is that you can view this kind of reduction as simply giving three algorithms. The first algorithm, part one, is the forward instance construction. It takes any input to the problem X and transforms it to an input of the problem Y, which we'll call Y super X. And this transformation needs to satisfy the property that if X is a yes input, then Y super X is a yes input. And this forward instance construction needs to run in polynomial time in the size of the input X. The next algorithm we're going to give is the backward certificate construction. This is going to take a yes certificate. Remember, a certificate easily verifies that that Y of X is a yes instance. It's going to take a yes certificate of Y x that corresponds to this instance x and transform it back into a yes certificate for the original problem x. And part 3 is the forward certificate construction. It's going to take a yes certificate for the problem x and transform it into a yes certificate of the corresponding problem y super x. And if you are able to provide these 3 algorithms, then you have a proof that x reduces in polynomial time to y. In particular, parts 2 and parts 3 are the if and only if proof that yes is that x is yes if and only if y super x is yes. And the next slide, we'll see exactly this proof in detail. Okay, so we want to see that if parts 1, parts 2, and parts 3 of this approach, these algorithms are all correct, then x reduces to y. Okay, so what we're going to do is we're going to give an algorithm for x, and then we're going to say that if x is yes, this algorithm outputs yes correctly, and if x is no, the algorithm outputs no correctly. So what is our algorithm for x? Well, we're just going to take x and map it to y super x using part 1 of our construction. Then we're going to run our algorithm for y on y super x, and if it outputs yes, we output yes, and if it outputs no, we output no. Okay, so that's our algorithm. And now let's see why this is giving the correct output for x. Well, let's suppose x is a yes instance. Well, if x is a yes input, then by part 3, the forward certificate construction, y super x is yes input. In other words, we can go from the yes certificate of x to the yes certificate of y. And therefore, and the algorithm outputs yes when y super x is a yes instance, and so therefore it outputs yes in this case. Cool. Let's suppose x is a no instance. Okay. Well, let's suppose now for contradiction that y super x is a yes instance. Okay. Well, if y super x is a yes instance, then by part 2, x must be a yes instance. But that's a contradiction because we assumed yes, x was a no instance. And therefore, it must have been that actually y super x was a no instance, and the algorithm outputs whatever is the correct answer for y super x, which in this case is no, and so the algorithm outputs no. And so again, we see if x is no, then the algorithm outputs no. Therefore, this is a correct algorithm for solving x, determining whether x is yes or no, and so it's a correct reduction. Okay, so that's our overview of hardness reductions. In the remainder of this lecture, we're going to see 3 reductions, reducing from 3-sat, the problem of determining yes or no whether a Boolean formula is satisfiable, to independent set, Hamiltonian cycle, and 3-dimensional matching. Talk to you soon.